trying to think of the best way to bring us in here. I think I'm going to do an example and then explain what happened instead of going the other way around, because this is one of those things that makes a lot more sense when you see it worked out. If we had the square root of 4 times the square root of 9, we can find these numbers. The square root of 4 is 2. The square root of 9 is 3. 2 times 3 is 6. So the answer is 6, which, by the way, is the square root of 36. What's 4 times 9? So we got this rule. When we're multiplying like radicals together, so a square root times a square root or a cube root times a cube root, they have to be the same. They have to be like radicals, just like terms have to be able to be combined only when they're like terms, like radicals. Square root and square root. We can combine it, since they both have the same radical, to be under one single radical. This works for multiplication. This works for division, not for addition and subtraction, just multiplication and division. So the square root of 4 times the square root of 9 would be the square root of 4 times 9, which would be the square root of 36, which would be 6. So in general, this is why I said this is easier to see with an example first. The square root of A times the square root of B is the square root of A times B. In fact, the nth root of A times the nth root of B is the nth root of A times B, because it works for cube roots, it works for fourth roots, it works for all roots, but they have to be the same. Likewise, the nth root of A divided by the nth root of B is the nth root of A divided by B. It's the product property of radicals and the quotient property of radicals. These rules are useful in this direction. To multiply radicals, you take the radical of the multiplication. To divide radicals, you take the radical of the division. Again, this doesn't work for addition or subtraction, just multiplication and division. But they're just as useful the other way. We can break up single radicals into multiplication or single radicals into division. What does that mean? let's say we had the square root of 24. Well, we know the square root of 25 is 5. We know the square root of 16 is 4. This is between 16 and 25. That means we can't do anything, right? It's not 4, it's not 5. Guess what? There's a lot of numbers in between 4 and 5. So it would be true because 24 is 2 times 12, and 24 is 3 times 8, and 24 is 4 times 6. That we could rewrite this any of these ways. And we could break up each of these into radical times radical. Only one of these serves any purpose. Which one do you think it would be? It's this one. Why? Because the square root of 4 is 2. If we're not breaking it up into a number that we can take a square root of, then there's zero benefit or need to break it up that way. We only want to break them up into ones that have perfect squares. Since 24 has a perfect square factor of 4, we can rewrite 24 as 4 times 6, which means the square root of 24 is the square root of 4 times the square root of 6, and the square root of 4 is 2. This is how we simplify a radical. If a number under a radical doesn't have a perfect square factor, then it can't be simplified. But if it does, then it can and must be simplified. Let's take a look at 6 times the square root of 56. Well, does 56 have any perfect square factors? Well, 56 divides by 4 evenly. "56 is 4 times 14. So see, I'm carrying the 6 all the way down. The square root of 56 becomes the square root of 4 times 14 because 4 is a perfect square factor. That square root now splits. Square root of 4 times square root of 14. I'm going to keep going down. 6 times the square root of 4 is 2 times the square root of 14. 6 times 2 is 12. So the final answer, 6 radical 56 is equal to 12 radical 14. Let's make this interesting. Oh God, they say. What's he gonna do? We have the square root of x to the 9th. Here's what our strategy is going to be. Let me show a long way that you wouldn't be doing this to explain why the short way works. Squares and square roots, they'll cancel. X to the 9th is like x squared times x squared times x squared times x squared times what? We're adding the exponents. So 2, 4, 6, 8. To get 9, we would need one more. And then if we split it, we'd have a bunch of square roots of x squareds and then one leftover x. We are assuming all variables are positive real numbers, so we don't need the absolute value multiple times, but this would be x times x times x times x times, oh, the square root of x. That one doesn't go because it didn't have a square left over. X times x times x times x is x to the 4th times the square root of x. Be careful that that 4 is part of the x and not making this look like a 4th root. X 4th root of x looks very similar to this, but it's not this. It's x to the 4th. There is an easier way to get to this final answer than splitting it up like that. Ask yourself, keeping in mind the examples we did earlier, ask yourself, what's the highest multiple of the root that fits in here? For instance, a square root, like an invisible 2 root. What's the highest multiple of 2 that we can fit into 9? 8. And rewriting x to the 9th would be x to the 8th times x. So let me change the color here so you can see that more clearly. X to the 9th is x to the 8th times x. Why did I want the highest multiple of 2? Well, that's what's going to make the next step work. We split this. We'd have radical x to the 8th times radical x. We can't do anything with the radical x, but what cancels with a square root? A square. And x to the 4th squared, just like those examples we did earlier, is x to the 8th. So when the square and the square root cancel, and we don't worry about absolute value because of our special instruction, we're just left with the x to the 4th. Let's look at another. The cube root of x to the 5th. What's the highest multiple of 3 that fits in 5? Well, that's 3 itself. How would we rewrite x to the 5th? With an x cubed, it would have to, since we add the exponents, 3 plus 2 is 5. We split cube root of x cubed, cube root of x squared. We can't simplify the cube root of x squared any, but the cube root of x cubed is just x. X cubed root of x squared. And in this one, make sure that you have it in as the cube root, not x cubed square root of x squared. These look very similar. So be careful with your exponent placement or your radical placement. This is x times the cube root of x squared. Let's look at one more. Let's look at the square root of a to the 11th. Square root, a 2 root. What's the highest multiple of 2 that fits into 11? 10. A to the 10th times a to the 1st, because 10 plus 1 is 11. Add the exponents. This is the square root of a to the 10th times the square root of a. Since a square root and a square cancel, we rewrite a to the 10th as a to the 5th squared. Leaves us with a to the 5th, and then we can't do anything with the square root of a. A to the 5th radical a. Let's have some fun with this. Woohoo. This isn't so bad. Fourth root of b to the 7th. Fourth root, we'd want multiples of 4. Highest multiple of 4 that fits into b to the 7th is 4 itself. Don't forget your fourth root. Fourth root of, we're adding the exponents. So 4 plus 3 is 7. Fourth root of b to the fourth times the fourth root of b cubed. Nothing we can do with the second thing, but fourth power, fourth root cancel out. B times the fourth root of b cubed. Cube root of w to the 7th, z to the 9th. And hold it. We've got multiple variables now. Well, we're going to assume that all variables represent positive real numbers, so we don't have to worry about the absolute value. And we're just going to do our little trick to both of the variables. So a cube root, we're looking for multiples of 3. The highest multiple of 3 that fits into 7 would be w to the 6th. And we'd need a w to the 1st. 6 plus 1 is 7. The highest multiple of 3 that fits into z to the 9th, that's 9 itself. So we don't have to split that one at all. We have the cube root of w to the 6th, the cube root of w, and the cube root of z to the 9th. Cube roots and cubes cancel each other out. Can't do anything with the middle one. Cube root and cube cancels each other out. W squared cubed gives us w to the 6th. Z cubed gives us z to the 9th. So this is w squared times the cube root of w times z cubed. And I'm going to go ahead and put the w squared z cubed in front of the cube root of w. We always leave our radical at the end, and if there was more than one piece that couldn't be simplified, we would end up combining those like radicals. Let's do another like this. The cube root of p to the 17th q to the 10th. Cube root means we're going to split highest multiple of 3 that fits in. Highest multiple of 3 that fits into 17. That's 15. P to the 15th times p squared adds the exponents to get p to the 17th. Highest multiple of 3 that fits into 10, that's going to be 9. Q to the 9th times q to the 1st, because 9 plus 1 adds the exponents to give 10. I'm going to go ahead and identify which factors are going to be perfect cubes, which ones are going to simplify. The reason I'm going to identify those is before the split up step, I'm going to make things a lot easier on ourselves by bringing the perfect, in this case, cubes, the perfect cubes to the front, and then everything else after. And we can keep this piece together now because they are the pieces that can't be simplified further. They'd end up combined in the end anyway. No reason to split them up. That might make this a little neater in these final steps. So we have our perfect cubed pieces that can be simplified times our leftover pieces that couldn't be simplified. A cube root and a cube cancels. Nothing can be done about that second piece. P to the 5th cubed would be p to the 15th because 5 times 3 is 15. Q cubed because 3 times 3 is 9. Gives us q to the 9th. And now we have our final answer. This cube and the cube root cancel each other out. We're left with p to the 5th. I'll write it up here. P to the 5th q cubed times the cube root of p squared q. If you need to break it up into more steps and then bring it together at the end, that's fine. But this should be the form of your final answer. P to the 5th q cubed times the cube root of p squared q. Let's put it all together. Assume that x, y, and z represent positive real numbers. And let's simplify the cube root of 250 x cubed y to the 5th z to the 7th. So if we were looking at the cube root of 250, we would be looking for factors that are perfect cubes. Perfect cubes, 1 is always 1. That's never important. So 2 cubed is 8. 3 cubed, 3 times 3 times 3 is 27. 4 cubed, 4 times 4 times 4 is 64. 5 cubed, 5 times 5 times 5 is 125. And that one, 125 times 2 gives us 250. So when we break things up into our perfect cube pieces and our leftover pieces, that's going to include the 250. So we'll break up the 250 if we need to. can. We'll break up the x cubed. We'll break up the y cubed, or y to the 5th. We'll break up the z to the 7th. Going to prepare all these markers. I'm going to try to make this the most color-coded example I've done, just so if there's something that's not falling into place for you yet, this might make it click. But I'm not going to be able to break this problem down more than I am here. So we have the cube root what are our perfect square or perfect cube pieces here? 250 is 125 times 2. X cubed. Highest multiple of 3 that fits into 3 is 3 itself. Y to the 5th. Highest multiple of 3 that fits into 5 is 3 itself. Y cubed, y squared is y to the 5th. 3 plus 2 is 5. And then for the z to the 7th, highest multiple of 3 that fits into 7 is 6. Z to the 6th. And that would be z to the 6th times z. Because 6 plus 1 is 7. Now, the things that we can take the cube roots of are perfect cubes. I'm going to bring those to the front. That's the 125, the x cubed, the y cubed, and the z to the 6th. Those are our perfect cube pieces. And then the things in red, those were our leftover pieces. The 2, the y squared, and the z. So when we split this, it's going to be the cube root of 125 x cubed y cubed z to the 6th times the cube root of the leftover piece, the stuff that can't get simplified, 2y squared z. If we take the cube roots of 125, x cubed, y cubed, and z squared, we get the cube root of a cube times the cube root of our leftover piece, the 2y squared z. what are the things that we cube? Well, 5 cubed is 125. X cubed is x cubed. Y cubed is y cubed, and z squared cubed is z to the 6th. So our answer, and again, this should just be our original problem, line 1, line 2, line 3, line 4, and then line 5 here, 5xyz squared times the cube root of 2y squared z. Well, this is going well. Hopefully the build up to this problem made it not so bad. Next, I want to do a quick few examples with the quotient property. So we haven't really done any there. If we have the square root of a to the 7th over a cubed, since a to the 7th over a cubed is a to the top minus bottom, 7 minus 3, a to the 4th. If we're assuming that a is a positive real number, then we end up with a squared. And how do we get that? Because again, a to the 4th is a squared squared. Square root and the square cancel each other out. Here's a fun one. Cube root of 3 over cube root of 81. As we get into the next lesson, we're going to see we don't want radicals on the bottom. We actually can't simplify either of these, but we can't leave it like this. We do have this property, though, that we can combine when we're multiplying or dividing radicals. So this is the cube root of 3 over 81, which is a fraction that can be reduced. 3 over 81, we can divide top and bottom by 3 and get 1 over 27. And guess what? Now we can re-split it. Cube root of 1 over the cube root of 27. Cube root of 1 is 1. Cube root of 27 is 3. So this is actually 1/3. We had to use this quotient property twice to get there. But just like with exponents, if we do correct things with radicals, we will get to the final answer eventually. Before we continue, I want to make a quick, I guess the word is correction. A correction, a clarification about the phrase like radicals. Now, up until now, I've let this slip into my vocabulary. And what I've been referring to as like radicals have been things like this that have the same root. These are actually not what we call like radicals. Like radicals are very much like terms, and we're going to talk about that in a second. These would be what we call radicals of the same index, the index being this number that tells us what root we're taking. So if these are just radicals of the same index, what are we specifically going to say like radicals are? There's the eraser. Well, like I said, like radicals are very similar to like terms. Like terms are the same variables raised to the same power. So 3x squared and negative 4x squared, those are like terms. We have 3 of them and we subtract 4 of them. Like radicals, exactly what it sounds like. Like radicals just means they are exactly the same radical. If we look at everything under the sign, it is exactly the same. And therefore, just like we can do 3 of these x squareds minus 4 of these x squareds to get negative 1x squared or just negative x squared. Like radicals can also be added and subtracted. 3 of these radical x plus 1s minus 2 of these radical x plus 1s would just leave us with 1, a single radical x plus 1. And this is going to be our introduction to the concept of adding and subtracting radicals. So last time we looked at simplifying radicals. Today we're going to look at how we can add and subtract them. And then we'll talk further about multiplying them as well. So let's do another one where I talk about them like they're like terms. So these are like radicals because they are exactly the same, square root of x. 3 of them plus 7 of them would give us how many of them? 10 of them. So 3 radical x plus 7 radical x equals 10 radical x, just like 3y plus 7y would be 10y. They work exactly the same. So we can't combine them unless the radicals are exactly the same. If we have 6 cube root of 11 minus 2 cube root of 11, are the radicals exactly the same? Yeah, they're both cube roots of 11. Then just like 6y minus 2y would be 4y, 6 cube root of 11 minus 2 cube root of 11 would be 4 cube root of 11. If we had radical 3 plus radical 3, this is not radical 6. Instead, just like x plus x would be 2x, radical 3 plus radical 3 would be 2 radical 3. One of them plus one of them is 2 of them. Just like x plus x equals 2x. How about this one? Radical x plus radical y. What's that? They're not the same radical. That's right. They're not the same radical. So we can't add them. This is the answer. We can't take it any further. It is absolutely not radical x plus y. Radical x plus radical y does not equal radical x plus y. Radical x times radical y equals radical xy, though. For multiplying, we are allowed to combine them. For adding, we cannot combine them. The only way we can combine when we're adding is if we have like radicals, and even then it doesn't combine underneath. What do I mean it doesn't combine underneath? Let's go back to radical x plus radical x. I said that that is 2 radical x. It is not radical x plus x. It's not radical 2x. Because 2 radical x, that would be the same as the square root of 4 times the square root of x. That 2 in front is coming from a square root of 4. So radical 4x is 2 radical x, not radical 2x. So this shows us we cannot add underneath for any reason. We do not get the same answer. Radical 2x is not the same as radical 4x. And radical 4x is the one that comes from the correct answer. So there's no way to combine radicals and add them underneath. The only way we can add radicals is thinking of them as like terms. And they add this way.